All right, today we're cracking open Earth's oldest and probably most valuable cookbook. We're going to uncover a recipe that's been simmering for, just a few 100 million years. Let's dive into the ultimate recipe for crude oil, the stuff that literally fuels our world. So, what exactly is this ancient recipe? Well, it's so much more than just a geological process. Think of it like a form of planetary cooking. It takes ingredients from ancient life and then transforms them under just incredible heat and pressure. And trust me, the cook time is absolutely staggering.
But first things first, when you picture where oil comes from, I need you to forget the dinosaurs. Seriously, that's probably one of the biggest myths out there. The real ingredients for this recipe are much, much smaller and way more plentiful than any T-Rex ever was.
You know, every great recipe starts with getting the right ingredients together. And for crude oil, that means we need to gather a massive amount of some very specific organic matter.
Here they are. The real source of oil is mostly ancient plankton and algae from the oceans. You get some contributions from land plants that get washed out to sea, sure, but forget dinosaurs. You need to be thinking about microscopic marine life dying and sinking to the ocean floor by the trillions.
Okay, but just like any fresh ingredient, all this organic stuff can decay and just disappear. So for our recipe to work, it has to be stored in a very specific kind of geological pantry, one that's going to preserve it for millions and millions of years. And this perfect pantry has a few key features. You need quiet, oxygen-poor waters. You need a steady rain of sediment to bury all that organic matter really quickly. And you need nutrient-rich zones that create those massive plankton blooms to begin with. Just picture these ancient, stagnant seafloors, or really deep lake beds.
Now, the anoxic conditions, this is the secret sauce. This is the most crucial part. See, without oxygen, the bacteria that normally decompose dead things just can't survive. And it's that lack of decay that allows all that organic goodness to get preserved and buried. It's an absolute game changer. So once our ingredients are gathered up and preserved, we can finally move to the prep stage. Now, we're not actually cooking just yet. First, we need to transform this raw organic sludge into a much more stable base.
The whole cooking process really happens in three main stages. We're going to start with digenesis. That's our prep work. Then comes catagenesis, which is where the real magic happens. And finally, metagenesis, which is basically what happens if you leave it in the oven for way too long. Okay, so during this first stage, diagenesis, our organic layer gets buried deeper and deeper and deeper. The sheer weight of kilometers of sediment sitting on top of it literally squeezes the water out and starts compacting it into something totally new. And the result is this stuff, kerogen. It's a solid, waxy, organic, rich substance. You should really think of it as the dough, or maybe the batter, of our recipe. It's the essential precursor, and it holds all the potential that will eventually become oil. Now, the crucial point here is the temperature. This entire prep stage happens at pretty low temperatures. We're talking less than 50 degrees Celsius. So it's more of a low and slow compaction than any kind of actual cooking. The real heat, that comes next. All right, our kerogen base is prepped and ready to go. Now it's time to turn up the heat and enter the most critical phase of our recipe, the main cooking stage. This is where it all happens. This stage is called catagenesis. As the kerogen gets buried even deeper, the heat and pressure become absolutely immense. And this causes something called thermal cracking, where these big, complex kerogen molecules are literally cracked apart into smaller, simpler molecules. We call those hydrocarbons, the basic building blocks of crude oil. I love how one source puts it. It says that the Earth's crust acts like a geologic kitchen. And in this kitchen, the kerogen is slowly cooked over millions of years, transforming from a solid wax into a liquid. But listen, this isn't a simple process at all. Just like any delicate recipe, the conditions have to be absolutely perfect. If you have too little heat, nothing happens. Too much heat, and you just burn the whole thing. So what is that perfect temperature? Well, the sweet spot for creating liquid oil is right between 60 and 150 degrees Celsius. This is the thermal range where that thermal cracking process is most efficient at producing petroleum. It's the Goldilocks zone. And that temperature is typically found at incredible depths. We're talking around 3 to 5 kilometers below the surface. The immense pressure at these depths also plays a totally critical role in this chemical transformation. So you take those precise conditions of temperature and pressure, and together they create what geologists call the oil window.
It's this very narrow window of opportunity, deep within the earth, where our recipe finally comes together. And that waxy kerogen becomes liquid crude oil.
But what happens if the burial just keeps going and the temperature rises above that perfect window? Well, like any recipe, you can definitely overcook it. Yeah, if the temperature goes past 150 degrees Celsius, we enter a whole new stage, metagenesis. The oil that just formed gets cracked even further, breaking down into the smallest possible hydrocarbon you can get, methane. And that is how most natural gas is formed. You've essentially overcooked the recipe and you get gas instead of oil. So we've gathered our ingredients, we've prepped our kerogen base, and we've cooked it perfectly inside the oil window. But the most astounding part of this entire recipe isn't the chemistry. It's the time. Just let's let this timeline sink in for a second. The journey from a dead piece of plankton to a solid chunk of kerogen, that can take around 10 million years. But to get from that kerogen to liquid crude oil, we're talking another 50 to over 100 million years of just slow, continuous cooking. This isn't just a long recipe. It operates on a truly mind-boggling geological timescale.
And that brings us to one final thought. Knowing that the fuel in your car is the end result of a 100-million-year-old recipe painstakingly cooked by the planet itself, what does that tell us about how we use it? It's a recipe we can't exactly speed up. Something to think about. Thanks for joining me.